Hello students, this is Mr. Allen, your calculus teacher. Today we are going to look at the product and quotient rules and some other things too. So this is section 2.3. So our objectives today are to find the derivatives of functions using the product rule, using the quotient rule. I'm going to share a couple of additional, derivatives for some trig functions. And we're also going to look at something called higher order derivatives. So we've already studied several rules for differentiation, and most seem pretty intuitive. For example, the sum and difference rule. So basically what this is saying is if I'm doing the derivative of a sum, it's just the sum of the derivatives. That seems very intuitive. Similarly, the derivative of a difference is the difference of the derivatives. So what about multiplication or finding a product of functions? What do you think that rule is? Now, I'm going to just take a leap here. Consider the function f of x equals x squared. Instead of calling it x squared, if you don't mind, I'm going to think of it as x times x. So I'm going to write it as a product. Now, I'm guessing, and I could be wrong, you may already know this, but if I asked you what is f prime of x, my guess is you'd say, well, Mr. Allen, it seems just intuitive that I'm going to just do the derivative of x times the derivative of x. In other words, the derivative of x is 1, and the derivative of x is 1. So the derivative of f prime here, or f prime, is just 1. I think that's what most students would guess. Unfortunately, that would be incorrect, and I would like to show you why that has to be incorrect. Let's go back to our original definition of this function, okay? If I have f of x equals x squared, then we know by the power rule that we've been studying that we just take the exponent times in the front, so we bring the 2 down, we leave the x alone, and then we subtract 1 from the exponent, so that becomes 1. In other words, the derivative of 2x. Now, does 2x equal 1? It does not. So what I'm trying to tell you is, or show you hopefully, is that this over here is incorrect thinking. This is not the product rule. It would be great if it was, but it is not. The product rule is a little bit more involved, and it's outlined on this slide right here. So the product rule for two functions being multiplied together is f times g prime plus g times f prime. Now, I like to give my students some hints on remembering those things, and I'll do that on the next slide, but I'm going to hold off on that right now. So let's say we wanted to find the product, or I'm sorry, find the derivative of h of x, which I have written here as a product. So if I'm going to do that, I could use our rule right back here. This is the product rule. And here's how that would break down. To find h prime, which is what we're trying to do, we're going to do f times g prime. That's g prime. That's the derivative of the second function, plus the second function times the derivative of the first. This is the product rule that we saw on this last slide. So let's go ahead and apply the product rule. And when we do that, first of all, we leave the first thing alone. But what is the derivative of 5 plus 4x? I'm going to get rid of all this writing on here. So what's the derivative of that? Well, that's 4. What's the derivative of this? Well, that's 3 minus 4x using the power rule. And then, of course, we want to clean that up. Let's use the distributive property in FOIL. And then once we got it all worked out here, we'll get negative 24x squared plus 4x plus 15. This is the solution to this particular problem. This is h prime. Now, here's a little tip if you think it will be hard to remember the rule, is I will tell my students if this is 1 and this is 2. Now, when I say 1 and 2, I'm saying the first term times the second term in a product. Then the derivative, I'll call it h prime here, is 1d2 plus 2d1. In other words, 1 is just the first term. d2, that's the derivative of the second term, so that's a product. Plus, there's that plus. 2, that's the second. times the derivative of the first. So this is a little trick, if you will, or shortcut or way for you to remember the product rule. So it's 1d2 plus 2d1. The quotient rule also is not as intuitive as you would hope that it would be. You would hope that the derivative of f of x over g of x would just be the derivative of f divided by the derivative of g. Again, unfortunately, that is not the case. So this derivative is actually g times f prime minus f times g prime divided by g of x squared. Now this one here, I'm just going to go ahead and give you the mnemonic device for this. Mnemonic device is just a saying that helps you remember something kind of like, please excuse my dear Aunt Sally. So if I want to do the derivative of, and I'm going to write this a little bit differently, I'm going to say high and then low. Okay, and high and low, just high means the function that's on the top, and low means the function that's on the bottom. So what's that going to be? So the derivative of high over low. So that's going to be low d high minus high d low over low low, or low squared. This is the mnemonic device that I teach my students. This is not, you don't write this down as your answer or anything like that. You might write it as a little scrap work to help you get the right answer. But this is just a maybe easier way to remember this formula. So it's low d high minus high d low over low low. That might be easier for you to remember. So let's look at an example of the quotient rule. Again, I'm just using very simple functions here, like 5x minus 2 this is our high function, and then x squared plus 1, that would be our low function. So if we're going to do the derivative of that, we're going to do low d high minus high d low over low low. Again, it's written right here. I'm going to use the formal definition. So this top function is the f function. The bottom function is the g function. So this is g times f prime minus f times g prime all over g squared. That's what we've got, okay? So that's based on our formula. That's what this is equal to, and this is a fraction, right? Okay. So there's all the work. We're obviously going to do the derivative of 5x minus 2, that's 5. Do the derivative of x squared plus 1, that's 2x. The bottom's just squared. Clean it up a little bit, clean it up some more, and that's your answer. So this would be y prime. This is an example using the quotient rule. Okay, so here's some of those trig functions. We already know the derivative of sine and cosine. And let's talk a little bit about the derivative of tangent. Now remember, the derivative of tangent, which by the way, tangent is the same thing as sine over cosine, right? So guess what rule we could apply to find that derivative? Well, we could do the quotient rule. We could say low derivative of high, oops, the derivative of high would just be cosine x, sorry about that, minus high, which is sine x. And then the derivative of low, the derivative of cosine is negative sine x, all over low squared. So that's cosine squared x. Now on the top, this minus and minus is going to become plus and positive, right? So on the top, what are you going to get? Well, you got cosine squared plus sine squared, and what's that equal to? Well, that's equal to 1. The bottom is cosine squared x. Well, what is 1 over cosine squared x? It's secant squared x. So I'm showing you this to illustrate where these come from. These didn't just fall out of the heavens. They're based on things we already know, and you could play the same game with these others. So here's just some examples. So if I wanted to do the derivative of y equals x minus tangent x, well, what's the derivative of x? That's 1. What's the derivative of tangent? That's secant squared. We just saw that. And of course, this one would be an example when you would need to use the product rule in addition to the derivative of secant. And the derivative of secant is secant x tangent x. Here are some more examples. So here's when you're doing the differentiation, and then here they are simplified. Okay, last thing we want to talk about today, higher order derivatives. So higher order derivatives, that's just a fancy way of saying, okay, you can do the first derivative, could you do it again? And the answer is yes. So this is the first derivative of the position function. We could do the second derivative, which we would call s double prime, or the second derivative of s. So those are higher order derivatives, and it turns out that the derivative of velocity is acceleration. So we would say that acceleration is the derivative of velocity. It's the second derivative of position. A function, the function given by a of t, the acceleration function, is the second. I just said that. The second derivative is an example of a higher order derivative. You can continue. You could go third derivative, fourth derivatives, etc. Now this slide here, I'm not going to go through this whole slide with you, but I'd like to note that there's a variety of ways that you can see derivatives written. I think I mentioned this in one of my previous presentations, but we could write it as y prime, we could say f prime of x, we could say dy dx, we could say the derivative with respect to x of the function f of x. And then this fourth one, I'm just going to kind of mark this out because I'll be honest, I don't know that I've ever seen it, but that's just a different way to write it. Now what I'd like you to notice is once you get past the third derivative, instead of writing 4 marks, notice that they do an exponent with parenthesis in there. I just want to point that out. You don't make 4 tick marks. You start using powers, like numbers like 4, 5, and 6. Oh, notice this as well. If you write it using this, this is like a difference quotient. The 4 goes on between the d and the y, and then the 4 down here goes after. That's commonly known notation for derivatives. Okay, finally, let's end it with a question involving some acceleration due to gravity. Because the moon has no atmosphere, a falling object on the moon encounters no air resistance. In 1971, the astronaut David Scott demonstrated that a feather and a hammer fall at the same rate on the moon. The position function for each of these falling objects is given as follows. That's the position function, where s of t is the height in meters and t is the time in seconds. What is the ratio of the Earth's gravitational force to the moon? So this is the position function for the moon, object falling on the moon. Okay, so here we go. There's our position function. If we do the derivative, we get the velocity function. So the derivative of this using our power rule is negative 1.62t. If we do our derivative again, that gives us negative 1.62. So this is the acceleration function. This is the moon's gravitational constant, and it's negative because it's pulling towards the center of the moon. So the acceleration due to the gravity on the moon is negative 1.62 meters per second. Now, hopefully you know, but maybe you don't, hopefully you know that the gravitational constant for the Earth is negative 9.8 when we're talking about meters per second. So if we want to know the ratio, which is what the question was asking us, for the Earth to the moon, we're going to do our negative 9.8 divided by negative 1.62. And it turns out that it's about 6. In other words, you could say that the ratio of the Earth's gravitational force to the moon is 6 times. Another way you could think of that is if you weighed, if someone weighed 120 pounds here on Earth, then that would be like 20 pounds on the moon, because that would be 1/6. All right, I think that's it. We'll call it a day.